Hello. During previous lectures, we have seen a couple of things. We saw Rubik's group. We saw symmetries of wallpaper. So what was Rubik's group? It was just a group of all permutations, all possible states of a Rubik's cube. So in that sense, Rubik's group or the Rubik's cube is very tangible representation of a group, of Rubik's group. You can touch it, you can feel it, and group is right there in your hand. All possible 4 into 10 to the power 19 states, more than that, they are just in your hand, right? Or the group of symmetries of wallpaper. Again, this picture is representing something. It is representing a group. This toy is again representing something, that is representing a group. So that is something. So Rubik's group is a tangible object. That occurs as a group. Naturally. So one of course has to understand what's the meaning of occurs. Occurs in the sense that the permutations which are there, all possible permutations, they form a group. But in one single toy you can see all possible permutations. Similarly, symmetries of wallpapers, given the wallpaper pattern, given say one tile, you have so many symmetries. So for example, rotation, reflection, and other things that I mentioned last time, glide reflection, all these things are there, and just through one picture you can understand about a group. So these are concrete examples of group. So concrete objects, these are concrete objects that represent a group. So concrete objects these are. And group, as we know, is an abstract structure. Through these examples, through the example of wallpaper symmetry, through the example of Rubik's group, that abstract group gets a meaning. It gets represented in a well, if you say real life situation. So for us, it's always good if we could represent a given abstract group in some meaningful fashion. So here the meaningful fashion was permutation, and here the meaningful representation was all this: rotation, reflection, light reflection, all these things. So here is something quite interesting. Any abstract group can be understood in terms of permutations. Any abstract group can be understood in terms of matrices. I hope you recall that for rotation and reflection yesterday we were talking about matrices. So these two keywords, permutations and matrices, they are quite concrete, right? And the statement is that any abstract group, what is abstract group? Any group that satisfies all those properties in the definition of group: associativity, existence of identity, existence of inverse. So any abstract group actually can be thought of as group of permutations. Any abstract group can be thought of as group of matrices, and that's quite relieving, that's quite interesting thing. So statement is, when you have an abstract group, then it can be thought of as if it is sitting inside Sn, a suitable permutation group. And that is called Cayley's theorem. So what is that? How can we realize any group as if it is sitting inside Sn? So here is this idea. You have a group, and to this group I want to associate some permutation Sn. So first question, what n should we take? So here I take n, which is same as the cardinality of G, number of elements of G. So here I am taking finite group. So here in this previous slide, it should have been finite group. Although for infinite groups also one can make similar statement, but let's keep finite because we want to keep Sn. So how do I associate a permutation to an abstract element, to a given element of group G? That's not very difficult. Let me just say that sigma goes, G goes to a permutation sigma G. A permutation is of n symbols. So what do I do? How do I define sigma? So sigma G is going to be a permutation, that is a bijection on G. And how do you give bijection on group? Using an element? Well, one way is you just permute in this fashion. You just multiply G from the left side, and it's clear that as a set map, sigma G is a bijection. How do we see that? It's just cancellation property. It's just left cancellation. So if I have sigma G, say H1, and sigma G H2, that means I am having GH1, GH2, both are equal. Existence of inverse allows me to cancel these. So G inverse G H1 is same as G inverse G H2, and therefore H1 is H2, and that means sigma G is a 1-1 map. So here is a 1-1 map which goes from a set, a finite set, to itself. So it has to be onto as well. There's a 1-1 onto map, that means it's a permutation, right? Any 1-1 onto map is a bijection. Bijection is precisely permutation. So this sigma G is actually permutation, and you can see that this is a group homomorphism. This kind of assignment is a group homomorphism, not very difficult to see. So therefore this is a homomorphism, and I claim that this is injection. So why should it be injection? So just check that if G1 is so if sigma G1 is same as sigma G2, then you just need to check that G1 is equal to G2. That's not very difficult to make out. So that's all. So what's the conclusion? Conclusion is that every group, every abstract group can be thought of as a group of permutations. So certainly for n is equal to size of G you can, but then in some cases you can also optimize this, you can also reduce this n. So this is just one algorithm, one way to see a group as a subgroup of permutations. So everything therefore can be thought of as permutation. So that's the message. Message is every element of a group can be thought of as a permutation. And now I am making another statement, namely every element of a group can be thought of as a matrix. So how to see that? Not very difficult. So statement is every element of a group can be thought of as a matrix. Not very difficult. When you can think of an element as a permutation, you can also think of it as permutation matrix. So what is permutation matrix? Well, you take identity matrix. Just I am giving an illustration of 3 by 3 case. And then what do? You just permute rows or columns. So here let's permute rows. So I have say 0, 1, 0, 0, 0, 1, 1, 0, 0. So what happens here? If I multiply this matrix to x-axis, so I am taking x, y, z, 3 axis. So x-axis corresponds to 1, 0, 0. What happens here? So when I multiply this, I get 0. I multiply this, I get 0. I multiply this one, last one, I get 1. So here x-axis goes to z-axis. What happens when I do the same calculation for y-axis? So x-axis goes to z-axis, and for y-axis what happens? So I get 1 here, and I get 0 here, I get 0 here. So matrix multiplication. So y-axis goes to x-axis. And what about z-axis? 0, 1, 0, 0, 0, 1, 1, 0, 0. So I am looking at z-axis 0, 0, 1, and when I multiply, what I get 0 here, I get 1 here, and I get 0 here. So z-axis goes to y-axis. So z axis goes to y axis. So this is a permutation. X goes to z, goes to y. So x, z, y, and then y comes back to x. So this matrix is actually representing a permutation. What is happening? First row of this is going to z, last row, third. Second row is going to first row, and then third row is going to second row. Third row is going to second row, that is z is going to y. So this matrix is actually representing a permutation. So these such matrices which are obtained after permuting rows or say columns of identity matrix, they are called permutation matrices. So they are obtained by permuting rows or columns of identity matrix. So you can apply a given permutation on rows or columns. So here is the thing, I can therefore give a map from Sn to group of matrices over a field, say complex numbers. So C is the set of a field of complex numbers, and GLNC is n by n matrices which are invertible. Those n by n matrices which are invertible, and it forms a group. So all permutation matrices being a permutation of identity matrix, permutation of rows or columns, their determinant is either +1 or -1, because you will be doing that permutation, that swapping of rows or columns either even number of times or odd number of times. So since the determinant is 1, matrix is invertible. So any sigma, any permutation can be performed on say rows of identity matrix, and therefore you get, let me just call it m sigma. M sigma is corresponding permutation matrix, and therefore this map is there, and you have to check that this map is a homomorphism. This is a homomorphism. You have to check whether it's homomorphism when sigma is permuted. Sigma permutes identity element as columns or rows. So that's a question. Okay. So for what notion of permutation matrices, whether it's in terms of rows or in terms of columns, this is a homomorphism. Nevertheless, so you have a homomorphism from here to here. It's actually injective homomorphism. So any group sits inside Sn and Sn sits inside GLN over a field, say complex numbers. So therefore every abstract group can be thought of as a permutation, and every abstract group can also be thought of as a matrix. So matrices and permutations, they were very concrete examples of elements of a group. So that's how these things are useful. So I am representing every abstract element as a permutation, I am representing every abstract element as a matrix. So that is quite possible. So with that, what becomes important are matrix groups. What's the advantage of considering elements as matrices, elements of an abstract group as matrices? When I have an abstract group, there is no structure to this element G. This G is atomic. But when I think of a matrix, so this is abstract, this is matrix, I can perform various operations on matrix itself. For example, I can compute its determinant, I can compute its trace, I can add up all the entries of it. So many things that I can do with matrix, but with an abstract element you can't. So in some cases it might be useful to think of an abstract group as actually matrix groups. So what are the examples of matrix groups? There are plenty of them, and in fact it's a whole theory of matrix groups. They can be thought of as what are called continuous groups, or say Lie groups, or in terms of algebraic geometry, or in terms of polynomial operations if you want to understand them, what are called algebraic groups. These are very rich theory of mathematics, having their own special place in mathematics. We are not going to talk about them, but we are going to just give some examples of linear groups. So what are the examples? I am saying first example that you already know of, GLNC. This is called general linear group. Of order n. And then SLNC. What's the definition of SLNC? Is those matrices, those elements in general linear group whose determinant is 1. So elements of determinant 1 form a group. So you take two matrices whose determinant is 1, the product is again determinant 1, and inverse of matrix whose determinant is 1 is again having determinant 1. So that forms a group. It's called spatial linear group. Few more groups. This group is ONC. What is this group? This group is all those matrices in GLNC for which MM transpose is identity matrix, n by n identity matrix. So here is an observation about such elements. Observation is that if you pick an element from ONC, then its determinant is either +1 or -1. This is because determinant of transpose of matrix is same as determinant of matrix, and therefore determinant of M square is just 1 unit. So this group is called orthogonal group, and in fact there is a geometric interpretation of this in terms of isometries. I am not going to say all this in detail, but this group can also be thought of, and in fact the general version of this is closely related to what is called isometry group for quadratic forms. It's quite interesting object, has its own theory. Okay, so elements of elements of ONC, elements of orthogonal group, therefore can be categorized into two types: the ones which have determinant +1 and the ones which have determinant -1. So the ones which have determinant +1 are called spatial, the collection is called spatial orthogonal group. So SONC. This is all those elements in ON for which determinant is 1 and this is spatial orthogonal group. There is a reason behind calling them spatial. I would come to that in a minute. In fact, one particular group which is SON over reals is what we are going to understand in later lectures in much detail, and that's going to be very nice application of group actions. So here's a remark, here is this remark, that quite often C is not important. C can be replaced by other fields, say reals or rationals, or what are called finite fields, fields which have finitely many elements, or there are some fields which have a number theoretic significance, say p-adic fields or local fields. There are so many fields, so you can replace them by different fields, and particular interest is there if field is that of real numbers. Then say in this case you have say SO and R that has a particular significance. You can geometrically see this again, and it occurs as group of rotations of sphere in Rn. So what is sphere in R3? The usual sphere that we imagine. What is sphere in R2? Circle. Yeah, the usual circle, say of sphere, or doesn't matter, you can say unit sphere which has radius 1. So that is of particular importance. Let me try to illustrate it for n is equal to 2 case. That is very easy illustration. So what's the condition there? SO2R, or another notation is simply you call it SO2, or you just call it SO2, R. So what's the condition? So condition is SO2 is collection of those elements. So M in let me write this time Gl2, and I am having R, SO2R, Gl2R. My field is that of reals, such that M transpose is 2 by 2 identity matrix, and determinant of M is 1. So let's try to understand what are all such matrices. So suppose I take a matrix A, B, C, D, which is lying here. So what's the property of that? Property is that A, B, C, D, when I multiply with its transpose A, C, B, D, it's going to have product to be 2 by 2 identity matrix. So what conditions do I get from this? So I multiply, I get A square plus B square here, and here I get C square plus D square. Therefore, both the elements are A square plus B square as well as C square plus D square are 1. Cos square theta plus sin square theta. Maybe in those terms you try to understand, and that's how rotations come into picture. What are other entries? So here I get AC plus BD, which has to be 0, and again here I get AC plus BD. So what are the conditions? Conditions are A square plus B square is equal to C square plus D square is identity. AC plus BD is 0, and there is one more quantity which is AD minus BC, which is a determinant, right? Determinant of this matrix, which is AD minus BC, that is 1. So this is what I get. So this is a condition for ABCD. So one can think of A as sine of something or cos of something. So I am saying cos of theta. So B will be sine theta, and let me think of C as say cos alpha. So then D will be say sine alpha. And what about other conditions? So when I write AC plus BD, so AC plus BD is cos theta cos alpha plus sin theta sin alpha, and that is 0. And what about other thing? AD minus BC, that is cos theta sin alpha minus so AD minus BC is sin theta cos alpha, that is also 0, right? So what is this? That means cos of theta minus alpha is 0, and from here I get that sine of theta minus alpha, oh sorry, this is 1, I'll just erase this, this is 1, the determinant. This is 1, so sine of theta minus alpha is 1, and when I make all these calculations, I eventually, when I solve all this, what I get is that sin alpha is cos theta, and eventually what I would get is that your matrix ABCD is essentially cos theta, and d is again cos theta, something like minus sin theta, and that is rotation matrix. So these elements can be thought of as rotation. So these conditions imply rotation, and even in the higher dimension these conditions indeed imply rotation. So this rotation which is happening. So in fact you can think of rotation in higher dimensions as well. And the remark that this rotation matrix cos theta minus sin theta cos theta, this matrix can be diagonalized over say complex numbers. We just treat them as complex entries, and what you have is e to the power 2 pi I theta, e to the power minus 2 pi I theta 0 0. That means these two matrices are conjugate to each other, provided you allow conjugation by complex numbers, conjugation by entries, by matrices which have entries in complex numbers. So in fact rotation in R2 can be thought of as complex multiplication. How is that? I can take say cos theta plus I sin theta, and then I can think of x plus iy for arbitrary element in R2. X comma y is being identified with x plus iy. So when I multiply, what do I get? I get for the real entry x cos theta minus y sin theta, plus the complex entry is y cos theta plus x sin theta, which is precisely what this matrix does. So complex multiplication can be thought of as rotation. We are going to talk about higher dimensional analog of complex multiplication in next lecture, and that is the case of quaternionic multiplication. Quaternions are certain objects, and we are going to learn all that in next lecture, and those quaternions are helpful in understanding rotation in not in R2 but R3. So what we have seen today, that abstract elements in group can be thought of as matrices, as permutations. They are useful in other things like rotations and all that, and there is a connection with complex multiplication. Next time we are going to talk about what is called a representation in a formal way, which is an attempt to make every element as a matrix, and there are certain applications, certain advantages of representations. We are going to talk about mathematical representations next time, but as of now I am sure you have understood that groups can be represented in various forms, in forms of puzzles, in forms of some permutation games, in form of some symmetry considerations. I showed you all those symmetric objects. So to know more about representations, watch for the next video. Thank you.